how many moles of ions are released. So you have to think about what's happening. This is kind of this idea of what's happening in an aqueous reaction or in an aqueous situation. And a compound like this, we first have to recognize as an ionic compound, cobalt-2 chloride. And then when that dissolves in water, it's going to become a cobalt-2 plus ion and 2 chloride ions. Right? All the ions break up in water. So we can kind of think of that as it's not exactly true from a molecular standpoint, but we can think of this as like one particle or one COCl2, one unit, and then this breaks up into 3 particles. So these types of questions deal with this idea of having something that is one thing and then it breaks up into more than one thing. So if you have 0.27 moles of this first thing, and this is where it's a little bit tricky to think about because you want to think of mole as a quantity like gram. And if it were grams and it broke up into pieces, it wouldn't matter, it would be the same. But moles is not a measured quantity like that, it's a count. It's a count of things. So if you have one thing and it breaks up into 3 things, then you've got 3 times as many things as you had initially. So if you start with 0.27 moles of this, how much are you going to end up with at the end? How would you find that? Yeah, so you can think of it like 0.27 moles COCl2. There's going to be 3 moles of ions for every 1 mole of formula unit of stuff. So you're going to have to multiply it by 3. Right, which is what? 0.8. So you see the 1 to 3. So you got to multiply that by 3. Next question is really the same question. The only thing that makes this one a little bit trickier is you have to recognize what the ions are. And to do that, you have to know your polyatomic ions. If you think of this as breaking up into atoms, like nitrogen, hydrogen, phosphorus, oxygen, you'd get a really big number. You'd get, what? 3 nitrogens, 12 hydrogens, a phosphorus, and 4 oxygens. That's not going to be correct here because that's not how this thing breaks up. So how does this thing break up? What's coming apart? Yeah. Go ahead. Yeah, ammonium and then phosphate. That's the ions. So how many ions are being produced when this thing dissolves? 4. Everybody see that? 3 ammoniums and 1 phosphate. So from 1.6 moles of one thing, we've got 4 times as many ions. So that's going to be D6.4 moles. So again, this is the kind of question where it's helpful to think about what's really happening, what's going on. All right. These next 2 questions are very similar, so see if we can do those as well. There's a little calculation involved here, but same idea. Think about what's actually happening. This is 4 ions produced. So it started with 4.6. Well, you have to think about what's happening with those things. So ionic compounds like that, valence compounds today. So like potassium chloride is KCl. So a mole of KCl right. You got KCl.
I went and dropped off in the tech. And then I went to work.
Well, what happens to KCl? What? Yeah, so how many ions? Oh, yeah, so you're gonna get 2 particles for every one, or 2 moles of particles for every one. KCl. So you think about that with the other ones as well. Okay. Yeah. No.
My last thing I got,
You got that flip, isn't it? Number 3 is
that
also
was the other cross.
because you've got 4 total particles, 4 total ions. So it's going to be 4. And the question is asking how many total ions it's all produced. That's the whole thing. On the bottom, right?
I was voting for myself. Not saying that you
So then moles of ions. Yeah, so it's going to be 4 moles of ions.
Very similar.
Yes.
It's so hard to do. It's ridiculous.
No, because this is
I have
also
and just
make sure you write out.
She's like a English teacher, probably for chemistry. My friend was assignment, it should be
But it's
she gotta be in.
1 mole of phosphate, 4 moles of ions.
She's in my math class.
This is 4 ions.
Yeah, she can even dumb it down like second grade. I can get what you're saying. I mean, but I was saying she was fixed, so. It's just my China nitric acid. Which one, where are you? Oh, nitric.
Okay. These are those things are going to dissolve in water.
Yeah.
It's like whatever they want to do. So
Yes, but it's so much more.
So I think it's
I'm taking material science, and that's what I'm not sure for, but it's been senior year. It's a whole
no, you should know that.
Yeah.
All right, let's take a look up at these first couple. I had a couple questions on ones like this. So I think you were right. Who asked me about this before? Was it? Somebody did, but I think this is wrong. This is supposed to be one or the other. All right. So this one's asking which produces the largest number of dissolved particles per mole. So again, when this goes into water, what happens and which one makes the most particles? So if something breaks up, it's going to make more particles than something that stays together. Which of these would not break up at all? Yeah, right, glucose. But glucose is not an ionic compound. And so if it's not ionic, it's not going to break apart in water. It's going to all stay together. It dissolves, but it all stays together. So that means it's going to be a one-to-one type relationship. 1 mole of glucose is going to make 1 mole of dissolved particles. The other ones are all going to break up and make more moles of dissolved particles than the original. So KCl, how many moles of dissolved particles does that make per mole of KCl? 2. And so then K2SO4 is going to make 3, and then ammonium phosphate 4. So which is the answer here? It's going to be D. That's going to make the most particles because that breaks up into 4 ions. Let's write that down. All right, same question again here. What's the answer in this one? What? A? Agree? Disagree? Yeah, A splits up into 3 ions. B is just 2. C is not ionic, so just 1. And D splits up into 2 ions as well. So A is the best answer. All right. So let's go back to these two that we looked at afterwards. This is the same idea, but now a calculation. We want to know not how many moles of HCl are present in this certain amount of hydrochloric acid, but how many moles of hydrogen ions. Sometimes that's going to be the same, sometimes it's going to be different. We have to know the formula to be able to figure that out. So first thing you have to know here is that the formula for HCl, or for hydrochloric acid, is HCl. I think everybody knows that one by now. Now we have to figure out how many moles of HCl are in there, and then how many moles of H are in HCl. So first, moles of HCl. We know we have 750 milliliters and 0.65 molar, which means 0.65 moles per liter. So we have to multiply the milliliters by the concentration. We have to convert to liters and multiply by the concentration to get that. So that is 0.750 liters. And then we've got 0.65 moles of HCl per liter, because that's molarity. That's what molarity means. Right, 0.75 times 0.65 is 0.49. 0.49 moles of HCl. All right. So now we have to ask ourselves, how many moles of H plus do we have per each mole of HCl? So it's kind of like the same question we've just been doing with the ions. Now we're dealing with H plus instead of some other kind of ion. So how many H pluses are in an HCl? Just 1. So that means there's going to be a 1-to-1 ratio. Every 1 mole of HCl produces 1 mole of hydrogen ions. So if we've got 0.49 moles of HCl, how many moles of hydrogen ions do we have? Same, right? So these types of problems require that you know the formula of what you're trying to figure out. So the second one, same question but with a different acid. What's the formula for nitric acid? Yeah, HNO3. So once again, you've got a 1-to-1 ratio. So all you have to do is multiply the volume by the concentration, and that's going to be the same answer because it's 1-to-1. So what is that? D, right? Or C? C. Yeah.
That first one, you
Yeah.
kept it as 1 liter under there because you have 0.75 milliliters. So you keep the units the same.
Right, because molarity is moles per 1 liter. So if it's 0.65 molar, if that's the concentration, that's 0.65 moles per 1 liter of solution. All right. So this type of question could be harder if we use a different kind of acid, or not harder, but different if we use a different kind of acid. So let's just try it. What if instead of nitric acid, this said sulfuric acid? What's the formula for sulfuric acid? Close. Yeah. H2SO4. The way to remember that, assuming you know the ions, is that if you know that sulfate SO4 is a 2- ion, then it's going to need 2 hydrogen ions to balance it out. Right? So now it's H2SO4. So now when this goes into solution, this is going to produce 2 hydrogen ions and the sulfate ion. So instead of just 1 hydrogen ion being produced in solution, it's now 2. So if you had 0.94 moles of sulfuric acid in solution, you'd have double that of hydrogen ions. Let's write that down. 0.94 moles of sulfuric acid would produce double that, which would be 1.88 moles of hydrogen ion. Because you've got 2 hydrogens per formula unit of H2SO4. Also, I didn't do it on this one because I wanted to focus on these things, but on the exam, what you might find, since we have more limited number of questions, is that in order to kind of ask a couple things at once, in a problem like this, I would maybe not give you the formula. So I could say how many moles of ions are released when 1.6 moles of ammonium phosphate is dissolved in water. You have to come up with the formula for ammonium phosphate, and then that would tell you how many particles that is. All right. So same type of question here. How many sodium ions are present in 325 milliliters of 0.850 molar sodium sulfate? Same idea. What are we gonna multiply this by at the end? If we figure out the number of moles of sodium sulfate, how do we get moles of sodium atoms? By 2, right? Because there's 2 sodium ions per sodium sulfate. Yep. All right. I'll let you go with some more now. But first, let's look at this one, because this is one we didn't really talk about in class. Electrical current. What's going to be a determinant? What's going to determine how well a solution can conduct electric currents? What? Not exactly, actually. Metal, it's true, metal conducts electricity very well, but in a solution, it's not the metal that necessarily does it. What is it?
Isn't it like something with a charge, but like you can do it by the periodic table, like how far apart goes in more with the
Kind of, yeah, but you're a little bit overthinking it for this part. It's actually just ions. It's another way of asking the same questions we've just been dealing with. The more ions in solution, the better the conductor, because the negative and positive ions are what have to conduct electricity. Like water, pure deionized water is not an electrical conductor, but like tap water is, because it has some ions in it. So in this question, between those 4 choices, which of those is going to conduct electric current best or at all? C, because that's the only ionic compound here. Does everybody see that? The others are all molecular or covalent because they don't have metal. So you were right to look for the metals, but just as a way of determining which one is ionic. Now we're going to look at the opposite question. Which is the lowest electrical conductivity? What do you think? which of those 5 is going to have the lowest electrical conductivity? What are we looking for? Yeah, the compound that does not produce ions or produces the fewest ions in solution. So what about A? Is A going to produce ions or not? Yeah, A will, because that's sodium hydroxide. That's an ionic compound. Anything with a metal in it, we can say is probably definitely ionic. So ionic. So we can probably cancel those off the list. What about the other 3? We've got ethanol, acetic acid, and what's that last one? Perchloric acid, right? So which one do you think is going to be the poorest conductor? Which one? B, ethanol. Why?
I honestly
Okay.
I just think.
All right. Other ideas? Agree? Disagree? Not sure. Maybe. Yeah, you're right. You're right. Actually, even if you didn't know why, it's because acids are also somewhat ionic in solution. Acids break up into ions in solution, right? HCl becomes H plus and Cl minus. Acetic acid also loses H plus. Perchloric acid also loses H plus. Now, those are weak acids, which means they don't break up as much as the strong acids like hydrochloric acid and sulfuric acid and nitric acid, but they still do make some ions in solution. We have a demo, I think we'll do it later in the semester, where we, actually, you know what, it's in a different class, but we can do it if you want, where we put a light bulb with like open terminals in some different solutions to see which ones are more conductive. And things like NaOH or KBr or HCl make the light bulb light up really bright because they conduct the electricity really well. If we put it in acetic acid or perchloric, we're not going to put it in perchloric acid because it's really dangerous, but we could put it in acetic acid and it would just light up the light bulb really dim because it does produce some ions, but not as many. Yeah, so the best answer here is ethanol. Ethanol is totally molecular, doesn't break up at all in solution. So would not be a good conductor. All right, the rest of these are stuff that we've been doing the last couple days. So go ahead and let's take another 20 minutes or so and work through more of these problems, see what you can do. Let me know if you get stuck. If a bunch of people are getting stuck around the same problems, we'll take another break and go through some. It's just random numbers because I pulled from some different things, and yeah, I didn't bother renumbering. Yeah.
For number 7,
Mhm.
so first I converted the milliliters to liters,
Right.
and then I plugged it into the molar mass ratio. So I minus that back and then got this.
Okay.
And then I put it by the 2 because there was only 2 ions for
Yep.
the solution. But then my answer was like
Yeah, because it doesn't say how many moles you said. So whatever you get for the moles, yeah.
It is that hard. It's like, but like NaCl, this table still like, you know.
So
That one's, maybe the one thing NaCl, that's yeah.
No, yeah. I mean, it doesn't matter.
Kind of.
Yeah.
That's why.
why are you using that again?
I mean, like, there's rules.
Because it's testing.
Especially for something like NaCl, so it's good.
Yeah.
Yeah.
See, yeah. I just looked it up. Someone said that it's,
It's not very.
You have to learn those psychological goals.
It can't be.
So the table is the one that's solid.
Do you have the, do we have the? I don't know.
It will, it is a will dissociate. It is not soluble. And it forms something.
Okay, so then last question on that.
Yeah.
So now that I have it in the 10 to the 23rd,
Right.
now do I have to multiply it by 2/1?
Right.
Okay,
Yep.
perfect.
The rest of them are stuff. And they can't just.
Is this gonna cover, cause I don't know, is this gonna cover like all the stuff? Like, is this gonna charge money to study off?
I mean, I put the other one in the notes.
Oh, that's all we have, that's all we have to know, that we. Okay.
That's a better way to do it than this because this is like, this makes it seem very use like.
Yeah,
Like
I didn't know, I
like,
thought we had to.
that one is just like a general rule. As long as you know that you're now, like there's always gonna be exceptions where you have to look up the solubility of something.
Yeah.
But for just like general, like on a test use, it's better to just know a couple of rules than to memorize like every single different thing.
Their class mentioned the.
Yeah. They won't open on the phone. What if you try from a regular browser instead of the Blackboard app? That might work better. If you want to pull a computer out, you can do that too.
So how do you know, like, they might answer, I didn't read the question, but how do you know when it's like the 2 and not, because the copper's not, it's not,
Right.
Right, so like
How do you know? In this question.
That's what I.
If it were just general, if it were just generally saying like whatever, you know, what, then you wouldn't. But there's a big clue in this question.
Okay, I didn't.
Yeah, read the question.
Thank you.
All right, I want to pause to point a couple things out here. There's a whole bunch of solubility type questions, and I've answered, I know, for a few people, do you need to know the solubility chart? And the answer is yes, but sort of with a but on it. Yes, you need to know the solubility chart. However, if you look at these questions, they tend not to be the weird exceptions. And I think you'll find that on the exam as well. So like 17, select the precipitate that forms when the following reactants are mixed. Here, I'll make this a little bit bigger. So you've got magnesium acetate and lithium hydroxide. They're going to switch places, right, and make magnesium hydroxide and lithium acetate. So what solubility rules can you use to figure that out? Or what did you? The hydroxide one? So the hydroxide one says most hydroxides are insoluble with a couple exceptions. And then there's another rule you could use to figure this out if you didn't remember that one. What's the other rule you could use to figure this out? The alkali metals, that's a big one. So alkali metal salts, the first column, are pretty much all soluble. Lithium, sodium, potassium. Right? So even if you didn't remember the hydroxide one, which has some exceptions to it, maybe you remember the alkali metals are always soluble And so then you'd know the other one. You know the lithium acetate couldn't be the precipitate, so it would have to be the magnesium hydroxide. I'm not saying it's always going to work that way. Same thing here. So you've got ammonium sulfide with copper 2 nitrate. We can write out that equation. All right, we switch places with the ions. You've got ammonium sulfide and copper 2 nitrate. Is copper 2 sulfide and ammonium nitrate? The sulfide rule, there is a sulfide rule on that chart, but again, it's kind of one of the weirder rules, has some exceptions and things. The other rules, ammonium salts are always soluble, nitrates are always soluble. So if you remembered either of those rules, you could get this question right. There are 3 different rules that would have led you to the correct answer. You didn't have to know all of them. You only had to know one of them. So that's kind of how I would take the solubility rules. Find the biggest, broadest rules and remember them. And if you don't remember all the exceptions that are kind of peppered in there, then, you know, at worst, maybe you get a question wrong or something. But you're going to get most of it just by knowing the general biggest rules. All right. So go ahead and keep going. We'll stop again. This is online too in the notes folder if you want to check it out later or do the answers.
Because carbonate is positive. Or wait, it's 2 negative, 2 minus 1. And sodium is plus 1.
when you're like setting these up to find the solubility of those, I'm a little confused on like whether to put the charge there or not. Like PB2, does it go PB2 SO4 or is it just PB SO4?
Well, what's the charge on those ions?
Well, this is a transition metal, right?
Right.
So it doesn't have one until you put
So what is it?
this is negative, isn't it?
Yeah.
So this is 2 technically then?
Right. So and
would
it doesn't
carry over.
change charge in a regular
Okay.
precipitation
So
reaction.
this does come to here then, so
No,
it's-
no,
oh, it
no, no.
doesn't?
The charge is +2. The charge is +2 here.
Okay,
You said the
yeah.
charge is still +2 here, but what's the charge on sulfate?
-2.
Right. So
Oh,
+2
okay.
and -2. You don't need any. You don't need to adjust those ratios.
Okay, cool. Thanks.
You have to think about the charges. In a precipitation reaction, charges don't change. So if it's +2 on the left side, it's +2 on the right. You have to adjust the subscripts so that the compounds are always neutral, but the charges don't change. So like in this one. So what happens? So NO3 is -1 and NA is +1. So that means now subscript size. So like this one, so you plus -2. So then you need to adjust the subscripts. Subscripts to that one, right? So yeah. So I'm gonna compromise sizes. That means that. So it's better to think about it balancing the charges on each side rather than the numbers. Because the numbers might change. You need to balance the equation.
Oh, just like the.
Yeah, but like CLO4, what's the oxidation number? So remember that chart, you like oxygen is there for chlorine. So you would say oxygen minus those two. And there's more of them. So that's -812. So what is not quite. +7 overall charges. 8 minus 7 plus.
You're more still soon. I'll go today. We're gonna do some more.
I don't know. Nobody says anything, but go ahead. We'll
That one was.
You can be there for a while.
Yeah, I just know both those.
Why is it not just CO3, CO4, 1?
Because cobalt is not +1.
Is it +2?
Yeah, because in this one, it's sulfate is -2, so cobalt has to be +2. And the charges don't change across, so yeah, so it stays +2.
Thank you.
All right, I want to look at one of these things here, and then we'll keep going. Well, I guess first, do you want to get into chapter 5 today, or do you want to just keep working on this stuff? Just keep working on this stuff? Okay, we'll do that. Also, there's a quiz scheduled for Tuesday, which is the day after the exam. I know that's weird, but we are going to do that just so we have enough quizzes so we can drop some. It'll just be the same material that's on the exam. Ideally, we would have the quiz before the exam, but because of the summer schedule, there's just no way for that to work. So that is what it's going to be. It's not going to have chapter 5 stuff on that quiz. All right, let's take a look at these types of questions. The book kind of makes it an issue of having a separate section for titrations. This idea where has anybody ever done a titration before? We're going to do some this year or this semester, but it's when you add an acid to a base or a base to an acid. Actually, it doesn't even have to be acids and bases. There's all kinds of titrations. But you add in a careful way to try to get to exactly the equivalence point. That is exactly when you have a perfect molar ratio of reactants. You know, we talked about limiting an excess reagent. If you do a titration properly, you're figuring out exactly the point where you have an equal amount of each, or the correct molar amount of each, a stoichiometric amount. So I don't think we need to think about titrations as a separate kind of problem. They're just a regular stoichiometry kind of problem, and you're solving for an unknown molar amount. And so this is like that. So let's take a look at how this would work. We're going to react sodium hydroxide and hydrochloric acid. So we write the equation first, sodium hydroxide and hydrochloric acid. And the products are water and NaCl. It's a neutralization reaction. And often in these types of reactions, these titrations, you're trying to find out an unknown concentration. So you have a known standard concentration of one of them, and you're trying to find the unknown concentration of the other. In this case, the known concentration is sodium hydroxide, which is given as 0.243 molar. And this is the unknown. That's what we're trying to solve for. What is the concentration of this one? We also know the amounts, 46.33 milliliters of this and 10.00 milliliters of this. That's usually how these things work. You take a volumetric pipette to measure a precise amount or a burette of the acid, and then you'd add the base to it until the stuff turns pink. We'll be doing that, I guess, next week probably. All right, so to figure out this, we have to recognize, first of all, is this equation balanced? Yeah, it is balanced, right? So that means 1 mole of sodium hydroxide reacts with 1 mole of acid. So however many moles we calculate for that sodium hydroxide, we should have the same number of moles of acid. So let's do that. 0.04633 liters times 0.243 moles per liter. Gives us 0.0112 moles of sodium hydroxide. So that's how many moles of sodium hydroxide we had to add. And since the equation's balanced and it's a 1-to-1 mole ratio, that's also the number of moles of HCl that would be there. Yeah.
Could you also use the M1V1 equation?
You can, but you have to be careful because that works for sodium hydroxide and hydrochloric acid titrations, but it's not general for other types. Because if there isn't a 1-to-1 ratio between the reactants, that doesn't work anymore. So, so yes, it would work in this case, but it doesn't always work. So that's why I don't usually talk about it that way. Okay, so that also means, since it's a 1-to-1 ratio, that we had 0.0112 moles of HCl. There had to be an equal molar amount because the equation's balanced. Now, if it weren't, if it were like 2-to-1 or something, then we just have to multiply it by a conversion factor, just like the other stoichiometry problems we've done. You have a question?
Yeah, I was curious that if it were, let's say, 2 moles of something.
Yeah.
By
Yeah, so you have to set up that molar ratio, just like we do with the stoichiometry problems, and multiply it. Yep. Or divide it, depending. Yeah. All right, so then the question isn't for moles, the question is the concentration. But we have moles, right? So now instead of a question mark here, we can say 0.0112 moles. And we have a volume, milliliters. So we can make a molarity, moles per liter. It's just going to be that divided by 0.01. And so we're going to get this. I'm going to write that out. 0.0112 moles per 0.010 liters. So we're close enough other than a rounding error there. Oh yeah, because I rounded this one wrong. That's the problem. 3, 3. All right, there's a couple other problems like this, so you can practice that. And then it goes on to, I think, or did I not put any more of those? It might be closer to the end of the paper here. Then there, oh yeah, here's a couple more. So then there are some oxidation number practice problems as well. So keep going and stop me or just call me over when you get stuck. And if I see a couple people being stuck on some stuff, then we'll talk about it.
Right. All right. So make sure that you got the numbers in the right place. So this is asking about concentration of gases. This is your concentration of sodium hydroxide. This is the volume of sodium hydroxide. So if you did that, you're finding moles of sodium hydroxide moves that now with the acid. So just make sure you're keeping it straight and wet. What a question was. You can draw a beaker with here's your sodium hydroxide. Here's the concentration.
It requires two.
Yes. Yes.
Because it takes
It goes with the oxygen, but all kind of together. So like we know the sodium get first priority, so those are each going to be +1. And the oxygens are each going to be -2. So you're right, the oxygens are -10 total. Sodiums are +2 total. So what's left is +8. So the sulfurs what? Okay. Yeah. So first, it's basically started with the same way that we just did the other iteration. So you got to find the yes, because you got to figure out how many moles of acetic acid were there. When you find moles of acetic acid, instead of then finding molarity, because you don't know the volume of the vinegar, you would convert that moles to grams and just divide by 5.54, and that would be the percent by weight.
And then for this one, I use.
Yeah, that doesn't work, right?
Would it be?
Well, you have to think about it. If you're going to multiply by 2 or you're going to divide by 2.
Okay.
Because depending on how you do that. If you can think it through, you can do it. But you got to think about like the concentration of. So if it were 1-to-1, you have moles of this and moles of this. It's 1-to-2, so you actually have half as many moles of the acid as you think you should if it's 1-to-1. So as long as you can keep that straight, that's fine.
Okay.
Yeah.
Great, it's acid is. You have to give us it. But that's part of the acid, that's the acid. That's half of what that is. It's taken.
No, you don't need that. You're going to start it the same way as any other integration. You want to find the only difference here is instead of using a concentration, but you still start out the same way you solve.
Yeah, well, we create
Yep. Right. Right. Well, anyway, and that's also acetic acid. So it's 8 grams of that.
So it's kind of.
So yeah.
So then, it's kind of, so I give it. Oh, thank you.
Okay, so first, I was. And then you're looking for 6%. And then you're just.
Yes, that's going to be your. Right, you have to find how much. So it's just like the opposite.
No, minus 40.
Okay.
Oh, it's minus 10. Oh, yeah.
Well, you have to think about the different ways that kind of force the reaction to occur. So you either make a precipitate, you make a gas, or you make water. Because you made water. Yep.
That's an acid base.
Right.
Yeah, that's what it says. Wouldn't it just be 0?
Joe, will you post the answer sheet of this later on?
No, I don't have that, but whatever you want to go through in class, we can go through the answers today. Yeah.
No, because I don't want my POs here. It's lost. Yeah.
I don't look at this one. I got a couple questions about it. This vinegar one. So this one, and this happens sometimes in questions where it kind of throws you off because it's asking it in a little bit different way, even though it's really kind of the same question to something you might already know how to do. I think that's kind of what happens here. We have a basic titration question. An acid is being neutralized by a base. And we know the amount and the concentration of one, and we have to find the amount of the other. The difference here is that instead of asking for a concentration at the end, well, instead of asking for a molarity at the end, it's asking for a percent by weight as the concentration, or percent by mass. And so that percent by weight or percent by mass is going to be grams of solute divided by grams of solution. That's what percent, times 100%. So we have a mass of our vinegar, a mass of the solution. So we need to find the mass of acetic acid in that to determine the concentration, the percent by mass. To do that, we still need to do this problem the same way. We have to set it up as a titration and look at the moles, but then we'll just convert from moles to grams. So that looks like this. Here's the equation. Acetic acid plus sodium hydroxide, water, sodium acetate. So again, it's a 1-to-1 ratio. We've got 30.10 milliliters of 0.100 molar NaOH. And then we want to know how much acetic acid there is. So we find the moles of sodium hydroxide, set that equal to moles of acetic acid, and then go from there. So we multiply the volume by the concentration. And that's how many moles of sodium hydroxide we have. Since it's 1-to-1, that's also the moles of acetic acid. And now once we get grams of acetic acid, we can get our mass percent. So there's our moles, and then we need grams per mole. So let's see, that's 24 plus 32 is 56, plus 4 is 60. Is that right? Anybody do this?
Yeah.
Is that right? Okay. Or 60.04 grams per mole. All right, so now we have a mass of acetic acid. We have a mass of total solution. We divide those and get our percentage. So 0.181, whoops, 0.181 divided by 5.54. All right, so it's about 3.27%, 3.26%. Yeah, sorry, I'm running out of room to finish the problem here. Yeah. All right, a 0.001 mole sample of calcium hydroxide requires 25 milliliters of aqueous HCl for neutralization. What is the concentration of the HCl? And this time they're giving you the equation, although it kind of got cut off from the thing here. But this is a good example of what, even if, so let's say they didn't give you that equation, and you just see like moles of one and milliliters, so you're going to do neutralization and get the other one. But this is an example where the M1B1 thing does not work. So because of the different molar ratio. So if you don't account for that, you'd get the wrong answer. So better to use the chemical equation. I'm just going to rewrite this over here. So we're given the moles of calcium hydroxide and the volume of HCl. And we got to make sure to keep those numbers straight. So moles of calcium hydroxide, volume of HCl. All right. So we need to know how many moles of HCl are in that volume, and then we can get the concentration. So in this case, we need to use the molar ratio because it's not 1:1, it's 1:2. We can say then 0.00100 moles of calcium hydroxide. And our molar ratio is 1 mole of calcium hydroxide, 2 moles of HCl. So we have to multiply that by 2 to get our moles of HCl. Now we've got the moles of HCl. The concentration is moles per liter. So that's going to be 0.00200 moles HCl divided by liters, which is 0.02500 liters from the 25 milliliters here. 0.08 molar. Should I just be a real pain in the ass and put none of the above as an answer on all the multiple choice questions so you're never really sure if you got it or not? That's a really mean thing to do. Because at least this way, if you didn't get any of the answers, you know, like you have to go back and check it.
Never put it.
But
Please never put it. It's like the worst thing.
sometimes it's necessary, but
It's not. You have the right answer instead of none of the above.
we're locked up here.
It's never necessary. Ever.
So what's the status like on this? Have you gotten through most of it yet, or still working? You take a break.
One after 41, can we go over that one? I don't know the number.
Oh, when it like skips numbers? Yeah, there is no number. Okay.
I wasn't sure if that was 42 or 52.
Doesn't really count. So.
Yeah, I don't know. The numbers are all over the place because I copied them from different places. All right, an important reaction sequence in the industrial production of nitric acid is the following. All right, so you've got two equations. Starting from 20 moles of nitrogen gas, how many moles of oxygen gas are required in the second one? So we need to do a couple different molar ratios here to work this out because there's a couple of reactions going on. So the first one, we know that our molar ratio in the first one is 1 to 2, so 1 nitrogen to 2 ammonia. And then in the second one, it's 4 ammonia for 5 oxygen. So we just need to set up two fractions that account for that. 20.0 moles of N2. We've got 1 mole of N2 for 2 moles of NH3. And then it's 4 moles of NH3 for 5 moles of oxygen. So 20 times 2, 5 divided by 4, 50. See how that works with the second molar ratio? So remember, I think part of the confusion here, those numbers that we have in the balanced equations are not necessarily like absolute amounts. That tells you a ratio that things react in. So it's not like we have to solve first for the ammonia and then we have to somehow convert that to 4 so that we can make 5. It's just a ratio. So as long as we keep our ratios straight, we're good. Since we're kind of unstructured today, just take breaks or whatever as you need it. And we'll keep working on this, and I can pull up more problems as you need. I'm going to go get some yogurt, so I'll be right back.
What if everyone's gone? I'm doing something hungry. Study on the plane. Yeah.
Oh, they would call it back.
I always do which is so dumb. Which is so dumb. And then I sleep like this. Because I have to sleep my medicine. Yeah. I lost my I don't know. I lost my I get lost so many things that year. I lost rings and I lost my like
I just
didn't
have.
mind, and I'm not sure. I must have been very like sad and stupid. But I like woke up in the morning with my glasses. And I was like, how did I do this?
Yeah. Is there any?
Yes.
Okay, so not, it's all, yeah, they're all right.
No oxidation. Windows oxidation. Windows oxidation. Just like which is the oxidation. Bye guys. Have a good weekend. Okay. Are you guys gonna start off with Good for you. None of us can eat, but yeah.
But
None of us can eat, yeah.
Or earlier, I don't really care what.
none of you can eat it? You could get some yogurt if you want. You still can't eat solid foods?
Yogurt, they don't have it in the menu.
Do they have it at the downstairs in the cafeteria?
It's fine, I'm just gonna finish this.
Okay.
Thanks.
What? Yeah, I saw one.
I feel like usually if there's an test, it must be up to, like, how do you know, like, if no reaction? So,
Yeah. So
I'll get us a table.
a couple people have asked that, so let's all talk about it together. All right, the question, I've gotten this a couple times, so let's talk about it. How do you know when it asks like what happens or what the product is if one of the choices is no reaction? Because that is often a choice. What are you looking for as far as knowing whether or not a reaction happens?
If it makes water,
Yep, if it makes water, makes gas, solid, precipitate. The other one is if it's a redox reaction. So like if it has changed oxidation states, that one we don't. I mean, there's lots of other answers to this question, but what we've done so far, the main ones to think about are those categories of reactions that we've talked about in class. So acid base, which forms water, precipitation, which forms solid, and gas evolution, which forms usually CO2 or SO2, something like that. And then also the redox reactions, the oxidation reduction. So if none of that stuff is happening, everything keeps its same oxidation state, everything, no water is being formed, whatever, then you could say probably no reaction has happened. That's often the way that question is asked is like, it looks like a regular double replacement reaction, but all of the products are soluble in water. So there's no precipitate or anything. And then you would say no reaction. In the example I have on here, where is it? There's a couple of them, yeah. So like this one here. So in this case, first what you should do is figure out the products on your own, because the answers might try to fool you there. But if you know, like, okay, barium hydroxide and nitric acid, they're going to switch partners. The H is going to go with the OH, and the barium is going to go with the nitrate. So that gives us H2O plus barium nitrate. And you might remember from the solubility rules that nitrates are always soluble. So barium nitrate is going to be soluble. And then water is liquid water. That's the kind of less reversible part of this reaction. So that's what you're looking for to see that it is something that happens. It's an acid-base reaction. And so B should be the answer here. Yeah. Yeah, let's look at the oxidation numbers. Like this one. All right, so this one we're going to use that other little table that we looked at on Tuesday, where we see what kind of atoms have priority, meaning that they're more likely to have a certain charge than others. In this example, we've got 3 different atoms: hydrogen, chlorine, and oxygen. And the rule goes, hydrogen is usually +1. So unless we have alkali metals, we assign our hydrogen as +1. Oxygen comes next on the list. Oxygen is usually -2. So unless it's in peroxide or unless like one of those other rules preempts it, oxygen's probably going to be +2 or -2. So that's -2, and there's 4 of them. So our total charge over here then is going to be -8, and then we've got +1 from the hydrogen. That's like so what does the chlorine have to be so that all ends up being neutral? 7. Yep, so it's going to be 7. Same thing here. Sodium metabisulfite. Anybody use that before? Anybody do any like brewing or making wine or any of that sort of thing? Use this as a way to stop the fermentation. But anyway, so you've got 3 atoms: sodium, sulfur, oxygen. What do the priorities look like here? Not quite. What's higher priority than oxygen? The sodium, because the alkali metals are always going to be +1. So the sodium will be +1, then the oxygen, you're right. Then the oxygen is -2, and then you figure out what's left. So each sodium's +1, that's +2. Each oxygen's -2, that's -10 overall. Yeah.
Sorry.
So we've got +1 for the sodium, and there's 2 of them. And then we've got -2 for the oxygen, and there's 5 of them. So that's a total of +2 and -10. So that means the 2 oxygens have to total +8. And since there's 2 of them, that's +4 times 2. Does that make sense?
Sulfur?
Yeah, sorry, sulfur. Yeah. So sulfur's got to be +4 so that it all balances out.
Okay.
Because there's 2 sulfurs. So.
Got it.
I'm sorry, do you want me to go eat it out there and then I'll
No,
come
it's
back?
fine.
Okay.
I was just shooting. No, it doesn't, no, I'm sorry, it's not it. I was just saying, but.
All right, so now we've got a typical stoichiometry type question. So one issue with this one, and I haven't done the calculation, so I'm not sure, is you'll notice that two masses are given, a mass of aluminum and a mass of oxygen, and it doesn't say anything about a limiting reactant. It doesn't say anything about find which one is limiting or find which one is in excess. Yeah, so you can't assume that this is a perfect stoichiometric mixture. You still have to check to see if one of those is limiting or not. So we're going to find moles of both of them. All right, so 82.49 grams of aluminum divided by 26.98 grams per mole. 3.057 moles. I'm just going to write that here so we've got it. And then 117.65 grams of oxygen divided by 32. 3.677. All right, so what do you think? Which one is limiting, probably? Yeah, aluminum is limiting, and we can do the calculation to figure that out. But you can see here, the equation tells us that it's supposed to react in a 4:3 ratio. But we actually have more oxygen than we have aluminum, right? More moles of oxygen than aluminum. So that's definitely not a 4:3 ratio. That's a 4 to something more than that. So that tells us the aluminum is our limiting one because we need less oxygen. And so, yeah.
When you have the 32 for oxygen, is that diatomic?
Right, because you got to use the whole formula. Yeah. All right, so we've got our moles of aluminum, and now we've got to figure out what mass of aluminum oxide can be formed. Now from that, the rest of the calculation is straightforward, but we had to first get the moles so we could figure out which one was limiting. All right, so now we can use that number, 3.057 moles of aluminum, and then we got 4 of aluminum per 2 aluminum oxide. And then finally, the mass of aluminum oxide, 101.96 grams per 1 mole. And so you can, I would assume, I bet, that the answer, if you would have started with the oxygen moles, if you would have started with this, I bet that answer is there too, and it's wrong. So that's why you have to make sure to find the limiting one, so you use that number in your calculation and not the other one. So here's another question, which is, it's the exact same question, just asked a different way. All right, so now this time, it's saying what is the limiting reactant and determine the mass of the excess reactant present when the reaction is complete. This is actually, even though there's an extra step here, this is kind of an easier question because it tells you that it's a limiting reactant situation, and you don't just have to know to look for that.
So for this one.
Yeah.
Is it, we're doing like, we're just replacing this with the other number, right? And then we do 1 to 3, right? Because it's, or,
No, yeah, right. So you're replacing that with the oxygen numbers
is
instead,
it, is,
and finding out how much oxygen you need.
I have it wrong there, so it's not 1 to 3 oxygen, or is it?
No, it's 4 to 3 because you got to go from this one to this one to figure out how much oxygen you need.
Oh,
We have the total.
So. How do you find your mass of the excess?
Let's do it. Let's check and see. All right, so how do you find the mass of the excess if this is the problem? Instead of finding the product, you're finding the excess. So we have to figure out, we start the same way. You know, you get your moles like we just did before to figure out which one's limiting. In this case, aluminum's limiting. Still limiting. So now we're going to use, what was that, 3.057? We're going to use that number to calculate how much oxygen we need for the reaction. So 3.057 moles of aluminum because it's a 4 to 3 ratio. And then times the molar mass again. So that's 32 grams of oxygen. All right, so 3.057 times 3 divided by 4, 32. And that's the grams of oxygen needed. Right. And then you just subtract it to find how much is left. So we actually had 117 grams of oxygen. So the difference between those is what's left over. Probably, yeah. So it's about 44 grams of oxygen remaining, 44.2 grams of oxygen. So D.
Let's do these.
Why does the equation start?
Because that's what we calculated up here for the amount of aluminum. These two questions happen to have the exact same numbers. So when you figure out the moles of aluminum using this mass and this molar mass, that's what you get, 3.057.
Why didn't we start out with 3.677?
The moles of oxygen? Because we figured out that that aluminum is the limiting reactant. So when you figure out which one's limiting, you have to start with that one. Yeah. So another answer to your question is this question can also sort of check you, because if you did do it wrong, if you did start with the wrong one, what you would find is that you have your calculation for the amount of aluminum that you needed. Let's just do it. It's going to be confusing if I just talk about it. So let's say we looked at these numbers, we didn't figure it out, or we were flustered because it was an exam, and we picked the wrong number. So we looked at these numbers and said, oh, oxygen's limiting, I'm going to use oxygen. Then we're going to calculate the amount of aluminum that we would need. Right? So calculating the amount of aluminum from the amount of oxygen would mean 3.677 moles times 4/3 for the molar ratio, and then times the mass of aluminum, which is 26.98. So we would get that we need 132 grams of aluminum for that mass of oxygen. The amount of aluminum we have is 82 grams. So we would need more than we have. So that means that aluminum cannot be the excess reagent, right? Because there is no excess. So we'd have negative excess. We have less than we need. So if you go the other way, that's what you'll find out, that you actually don't have any excess. You have less than you need, and that's a sign that you did it backwards, that you used the wrong one. You picked the wrong limiting reactant. So you go back and do it again. Does that sort of work?
So when you did it that way, you put 677 times.
Yeah, because it's 4 aluminum for 3 oxygen.
Thank you.
Yep, see you Monday.
So for that one,
Yeah, for that one, because that's a different question. But I'm saying if we were doing this bottom one, if you did this and you simply use this number to solve for aluminum oxide, you just get the wrong answer, and there wouldn't be a nice way for you to check yourself. This bottom one would give you that way to check yourself.
Are you sure that
There's not none of the
the
elements.
ratio is right? And your ratio is still up there?
Because H still has the wireless. Other switches. Yeah. So like the redox doesn't.
Which would make sense. Okay. Yeah, yeah, okay, yeah, definitely, yeah. Okay. You good, you good.
I would just.
It's the same. Yeah. Numbers, yes, that easy on there. And then we start back. So like maybe times the ratio.
Alright, check.
It's 3/2. We're changing it to magnesium.
I can look at this.
I was experiencing this. Like cancels out. Sorry, I like physics. It's just 80 times easier to not mistake.
That was a volume that. Right, I haven't posted those yet. The quizzes are up in master chemistry, but they're not. Yeah, because there's only been like one thing, so. Yeah. Don't worry about that. I'll make sure everything gets updated when I create the exam, so that you have like everything up for the first.
You have to.
Before.
So I multiplied it by the ratio and then multiplied it by the mass. Yeah. Yes. So now your grams of magnesium is used. Oh, yeah. And then you subtract it. I got that. So if we're given like in 56, it's like the answer is 1.65, but all the answers aren't whole numbers. You just round out, right? Like all of these are whole numbers, but that's. How is that not it? Putting gram to ratio mass. And you subtract.
Yeah, I can see this.
Is it the right? I think it's the right.
Let me do it and see.
I might have wrote something down.
Yeah, I think you're right. I get the same thing. It's just rounded. Yeah, it probably shouldn't be rounded like that.
Okay, so I set the formula and then I converted these to moles and this to moles.
Yep.
I must have done something wrong down here. I'm allowed to start with this or the limiting reactant.
You got to find which one's limiting.
This one's limiting, right? Because it's the smaller one.
No, not necessarily. I mean, I think that is true, but you have to, based on the molar ratio, because there's supposed to be 3 of these for 2 of these.
Oh, right.
So you got to check if this is,
Smaller if we multiply by 4.
if you multiply by 3 and divide by 2, do you get something bigger or smaller than that? It's that like 3/2 ratio.
And that's how you find it.
Right.
Let me do that now.
No. Isn't it 10 for 1? Yes. No, yeah.
And you have to do that because it's not a 1-to-1 ratio.
That's right. So you have
would
to
do
check
for
that
normal
ratio.
limiting problems
Yep,
anyway.
always.
Okay, so then
So you find a number that is bigger or smaller than this. It's smaller, right?
smaller. So this is limiting.
So
So
that
I
means that this
should
one
use
is
this
limiting
one.
and this one is in excess.
Okay, so I'm using this number and then doing this equation.
Yes, you're using the wrong number, right? So you need to start with the iron and then go from there.
And see if that works.
You
Is
have to
this
change your ratio too, because it's 2 to
perfect?
3.
Okay, so
Yep.
then that should make sense. Sweet.
Yep.
Okay, thank you.
Is the exam going to be split up pretty equally between the chapters, or is it going to be?
No, I would say it's going to be, it's going to be bigger in 3 and 4. You know, the naming, the equations, the calculations, because we can kind of fit the other stuff in there, the conversions and things. Yeah.
Catching fast by science. Oh, no. Like I said, I started. yields what you actually got or what you should have got.
Right.
Okay, so we would just recognize in this case, this will recognize of this with the experiment. And we divide it by or to get the well, what's theoretical? What do you find theoretical?
Theoretical is like what you calculate from the molar ratios in the equation.
Could you do 59?
The actual is like what you got when you actually did the experiment. They don't give you? They have to. Which one? 59?
59.
Yeah, so
We find the theoretical, but
right, so you start with 75.3 grams of this. Yeah. So then you're going to calculate some theoretical, and then this is the amount that they actually produced.
So am I supposed to flip flop this?
No.
Count to like a really large, count to like 300 something.
Is that the right number? Which one is
I
this?
think so, 55.
56. Oh, because you use the wrong number because this is iron chloride, and that's going to cancel. So this is going to be magnesium chloride. Make sure you write out all your units. So it's grams of magnesium chloride per mole, but that's not the mass of magnesium chloride. Magnesium chloride's 95.21.
Oh, so this is
yeah.
95.21 grams of magnesium chloride.
Yep.
There is no.
So then magnesium and then 1 mole of magnesium chloride.
Right.
So then that cancels. So I just used the wrong thing.
Yeah. This one? For 56? All right, let's see. So, all right, so for 56 here, I calculated the moles of each of these from the grams that were given. So 41 divided by this, and then 175 divided by this. That gives me the 2 moles. So then I have to figure out which one's limiting. Which one isn't limiting and which one's in excess. So you got to look at the molar ratio of 3 to 2 or 2 to 3. We need 3 over 2, 3 halves as much, 1.5 times as much magnesium as iron chloride here. So if I said like 1.08 times 3 divided by 2, the molar ratio there, I get 1.62. So that's how much magnesium I need in moles. How much I have is 1.69 moles. So that means that the iron chloride is limiting and the magnesium is in excess. So I'm going to use my iron chloride numbers to do the rest of the stuff. Well, I could go the other way too. If I wanted to start with 1.69, then it's 2 over 3 because it's 2 iron chlorides for 3 magnesiums. And then that shows me that, oh, I actually need more iron chloride than I have. So iron chloride is the limiting reagent. Right. Right.
So I got like a ridiculous number with this. It was like 200 something.
Let's see. That's for, are you doing the first one?
Yeah.
All right, let me see. So this is limiting.
Mm-hmm.
Oh, maybe that's not the right. You're starting with the wrong number. You start with that number.
Oh.
Because this was just checking to see if it was limiting, but that's the actual amount that's there.
Okay. Perfect.
figuring out for 3, is that the 3 as in for just magnesium, or is that 3 as in for magnesium chloride?
Depends what you're doing here. Maybe grab another piece of paper so you can write this out more clearly, but no, I think it's here because you're saying this times 2 of these divided by 3 of these, and that gives you how much of this one you would need.
Okay, because I was looking at it sort of like the equation we had where we did the one that we did where we took the entire this one we did the we did one. Let me go back to the check.
Yeah. Okay.
$57. Is this the right equation?
Yeah.
Okay.
Well, it's not balanced though. Because you don't have a 2 here. Yeah.
Would that affect?
Yes.
Oh, yeah, because I did see.
That would change your molar ratio too. Yeah.
Can you work through 60?
Yep. Number 60, this one?
Yeah.
Okay, yeah, let's go through it. All right, so we're gonna start the same way, find the moles of each one, and then find the limiting reactant. This is a 1-to-1, this is a balanced equation already, so we don't have any molar ratios to deal with. So let's calculate that. 119.3 divided by 208.2, 0.573. moles. And then the chlorine, 61.3 divided by 70.91, 0.864 moles.
Wait, the 0.573 is the product, right?
Oh, sorry, yes, sorry.
That's where, yeah.
So that's why you're confused. Okay. That's right though, right? Yeah.
Yes.
Okay. So I forgot the other number already. Do it again.
The grams.
Oh, okay, I see, okay. All right, so we don't need that right now. We'll deal with that in a second. So we know the amount of chlorine, and then it says react with excess PCl3. So you can say as much as you need. That's what excess means. You have plenty. So that means that we can calculate the theoretical yield based on this number, this 8.864. Since it's a 1-to-1 ratio, that means that we should make 0.864 moles of this too. You see that? Because the equation shows us 1 mole of chlorine makes 1 mole of PCl5. So yeah, so that's the theoretical yield. If we multiply that by the molar mass, we'd get that the theoretical yield is 103.1 grams. So the actual yield is wait, something's wrong here. Yeah, okay, 179.9. Okay, that makes more sense. So the actual yield was 119.3. The theoretical yield is 179.9. So the percent yield is 119.3 divided by 179.9 times 100%. $66.3%.
No. Yeah, because you're.
See my name. Yeah. Yeah. So if we did that all out, we would find 0.864 moles of Cl2. Is it okay if I start there? Do you see how I got that number? Okay. Then we're going to go from moles of Cl2 to moles of PCl5. And that's 1-to-1 based on the equation. You see that? And then grams of PCl5 per moles of PCl5, which is the molar mass. So that's 208.2 per 1 mole. And that gets us the theoretical yield, so 179.9. And that's grams PCl5. You have a question? Or are you just pointing at things? Okay.
So like this page, it's a digit because it gains electrons here. Goes from
Yes, that's right. Yes. Yeah.
So, what are the gases CO2?
Yep.
So like
That'll change. No, because it depends on the ratio. So you get, it's easiest to get a ratio of 2. So say you did this and this came out to like 3. Then this one would be at least 6.
The ratio and the max.
Less than 6. Yeah. So that one, this is right. So that's what it's 7 divided by. Yeah, so about less than 0.1. So that tells you the test twice as much of this as you have of this. If you have
Right.
that, twice of that. Right, so you need what, 1.7 tests for that much more.
I hear this. Yeah, I did the whole test. Yeah, I divided this. Well, no, you did yours. It doesn't matter.
Right.
Yeah. Yeah, no, so what did you do?
Yep.
So you can use this number. Yeah. Times C.
Oh.
95.
Let's take a look at this last one because it's a little bit different. Has anybody done this one yet? Okay. The difference here is that we're dealing with solutions instead of solids. So we have to calculate moles from molarity and volume instead of from grams. So let's take a look at this. First, you still want to write out the equation just like you did before. Balanced, yeah. All right. So 38 milliliters of 0.5 molar copper chloride mixed with 42 milliliters of 0.6 molar ammonium sulfide. Same thing, we got to calculate the moles and figure out if one of these is limiting and which one. Normally, when we have grams, we calculate moles by dividing by the molar mass. But this time we have volumes of concentration. So the copper chloride is 38 milliliters of a 0.5 molar solution. So to get the moles there, we're going to go 0.0380 liters times 0.5 moles per liter. That's copper chloride. And then the other one is going to be 42 milliliters. All right, so which one's limiting in this case? Yeah, it's got to be that first one because the chemical equation gives us a 1-to-1 ratio. So these are easy because we don't have to check that molar ratio.
So if it's like a 2-to-1 ratio, you
Yeah.
multiply the CL2 by 2.
Right.
Okay, and if it ends up being more than the second one, then the second one's limited?
Right.
Okay.
Yep. All right, so then or wait, yeah, so if this were 2 and this one were 1, we'd have to multiply this number by 2 because you need twice as much of this as this.
Okay.
Oh yeah, thanks. So then the rest of it says, what is the maximum mass of copper sulfide formed? So we're going to use the smaller number, the limiting one. And since it's a 1-to-1 ratio, that means we also form 0.0190 moles of that. So then to get the product, we just need to convert that to grams. So 0.0190 moles of copper sulfide times the molar mass, which is going to be 95.5 or so. So same idea, you got to get moles, figure out which one's limiting, and then solve from that. Wednesday. They're both going to be due on Wednesday. Yep.
Thank you.
Yep. The what? The end of 56. Yeah. Okay. So you figure out the moles of each one, right? And then figure out which one's limiting. Let's see, in this case, it's not obvious. So let's see, 1.69 times 2 divided by 3 is 1.12. Iron needed. So that means the iron chloride must be limiting. Is that what you found? All right. So that one's limiting. So then we can use those moles to figure out the amount of magnesium that is needed, right? So let's do that. So 1.08 moles times 3 divided by 2, 1.62 needed. 6. So the difference between those two is the excess. So we can convert that excess to grams. It's 0.07 moles. 0.07 moles times the molar mass of magnesium, 24.31. The difference between 1.69 and 1.62. And so it's 1.7, or about 2 grams.
For this equation, when you balance it,
Yeah.
where are the two, just to double check.
Because we've got 2 ammonias on this side and 2 chlorines on this side, so we need 2 of each of those on that side too.
So when we're doing the double displacement reactions, is there a way to know for sure what happens with these?
You have to balance the reaction. So just make the compounds on either side. Like sulfide is a 2- ion, so ammonium sulfide has to have 2 ammoniums per sulfide. Because ammonium is +1 and sulfide is -2. Right. So then on the other side, chloride is -1 and ammonium is +1. So there's just 1-to-1 ratio. So when you build that compound of ammonium chloride, you only have 1 of each, +1, -1.
So, okay, because when I look at it just here, like NH4 is negative, that's a negative.
+1.
Just +1. And then ammonium is
+1.
It's a CL is -1. So it looks like it balances, but because I have 2.
Yeah, you still have to balance the chemical equation. So you've got 2 chlorides on this side, you need 2 on this side, so you got to put 2 out in front to do that.
Because there's also the 2 ammoniums
Right.
right there. Okay. And
You may want to practice some more. Just make sure you're balancing. Do a lot of balancing equations practice. Chapter 3.
I didn't want to go that stuff. Okay, yeah, I was trying to get all the chapters. Now I see that you had 0.19 somewhere, 0.019. Is that by having this number? That's not 0.01.
And that question, let's pull that one up again. Let's see.
Or maybe is that 78? Yeah, this is 78. Let's do it.
Oh yeah, so that's the number of moles of copper chloride.
Because
There's 38 milliliters, and that's the concentration, 0.5 molar.
so you basically take the 0.038
Yep.
and multiply it by the molar concentration.
Yeah, the moles per liter to get moles.
Okay.
So liters cancel, and you get moles.
Okay. So all these molarity things are always per liter.
Yeah.
Okay.
That's the definition of molarity, moles per liter.
So when you have a 0.500 mole, is that as in like half
That's
of-
molar. Molar, moles per liter. That's molarity.
Okay.
Yeah.
Just
It's a measure of concentration.
Is the abbreviation the same for molarity as it is for mole?
No, moles are MOL.
Okay. This I was looking at there, I was a little bit confused.
Because molarity is moles per liter, and moles is moles. Molarity is a concentration.
Because I was reading that as 0.500 moles.
No, it's moles per liter. It's a concentration.
Got it.
Usually they give us like the grams, but
Mhm.
it says you find the limiting reactant.
Yep.
But they give us moles.
Yeah, so that makes it easier because then you don't have to convert to moles first. Because the
Oh,
equation
okay.
tells us it should be a 2 to 1 ratio.
Mhm.
If it's a 2 to 2 ratio, then which one's limiting?
This one.
Yeah.
NA.
Yeah, because if you have 2 of these, you need 1 of these.
Right. So
But if you have 2, that means
You
there's
have
excess.
4.
Yeah, you'd have to have 4 of the other one, right?
Wait, Joe, we're still confused on
Okay.
how you got that.
Which part? This one? Where did I get? Oh, on the other one? This one? I use the molar ratio from this one, so let me write that out. So I'd go 1.08 moles of iron chloride. And then the equation tells us that if I want to go from this to this one, it's 3 to 2. Oops, 6-2. Did I do that right?
Or I ended it,
Oh, yeah. Oh, yeah,
okay.
so then what did you do after you got the 120?
All right, so then since this one is in excess,
Where's the 1.69? Oh.
that's given in the problem.
Oh.
41 divided by 24.31. That's the amount that we have, like at the beginning of the reaction.
Okay, and then all you have to do is just subtract the 6.
Right, so whatever is needed for the reaction, and whatever is extra is the remaining, the leftover stuff, the excess.
So the equation where you took that 0.07 difference and did something with it, which equation, which problem was that again?
Right here. So that's because that's what it asks. It asks for the mass. It doesn't ask for moles. So I have to convert that 0.07 moles to a mass of magnesium using the molar mass.
So I would take the molar mass of magnesium, that's 24.30.
Yeah.
I would multiply it by 0.07.
Right, because that's the difference here. That's the difference in moles.
Okay. So that would get me to 0.30. And that would be the weight in grams that we need.
Of remaining that's not used in the reaction.
Okay. All right. I don't.
On the test, are there like questions about lab and all?
Not really. I mean, not like what was step 4 of just like,
Understanding.
yeah, something about lab might come into a question. You wouldn't need to you don't need to go back and study everything that we did in lab.
Okay.
Yeah.
So this was our 1.69,
Okay.
right? And then
Yep.
this was our 1.62.
Okay.
So then we subtract and we got 0.7.
0.07.
0.07. That's why. And then we had to multiply that by that, so we forgot a 0.
Yeah.
We just forgot a 0. It was 0.07, not 0.7.
Yeah, left some of those zeros out.
See, for that one, we started out the equation just doing it 1.69 moles of magnesium over to.
Yeah, but that's not going to work because magnesium in this case is not the limiting reactant.
Right. So in order to get the right one, I would figure out I was doing it incorrectly just by what I got here.
Right, because it wouldn't make sense because you get more than what you needed.
Okay. Yeah, because I was, as you were doing the problem, I was trying to do it too, and that's why I stopped.
Okay.
And I realized, you know what, this isn't going to, because I kind of just abruptly left it. So I should have started out with 1.08 moles for the iron chloride, or iron.
Right.
Okay.
All right. All right. See you Monday.
How long do we have for these?
The full time, so whatever, 3 hours.
3 hours?
Yeah.
Does it generally take that long?
No.
For you, but-
Well, I usually write it. I would say the average student will take like 1.5 to 2 hours on it. Some people will be done a lot faster. Some people will take longer.
Okay. How representative of the test is this?
This is not. This is just a few questions from chapters 3 and 4. Mostly chapter 4. So the test will be a lot broader than this. So you definitely want to do plan on doing all of the questions from each chapter. You know, just open your book up, and do all the homework from chapters 1 through 4, and that will cover pretty much everything that would be on the exam.
Okay, because I was actually doing the homework. I started the homework for chapter 3, and then I had started. I thought I had almost finished it, and I looked up and I'm like, it was 2 o'clock, and I think I only got credit for 10%.
If that happens, you can still finish it up and just let me know the next day, and I can move it back.
Oh,
but yeah. But I'm talking about. I'm not talking about the Mastering Chemistry. I'm talking about the Mastering Chemistry is just a small sample of problems. I would say, if you really want to know what's going to be on the exam, do all the problems from the book, from all 4 chapters.
For the homework for 3, can you move that back so I can actually get the credit for the things I did do?
Yeah.
I started and I was going through a lot of the problems, and then I looked up and I'm like, they're only giving me credit for